Edexcel Decision 1, Graphs and Networks 3, Planarity and Floyd's Algorithms. Floyd's algorithm, interpreting the results. As we know from previous videos, Floyd's algorithm finds the shortest path between all the pairs of vertices in a given network. This is the network that we have looked at, and we use this network to find the shortest path between all the vertices. We found a final distance matrix and a root matrix. Okay, so these are the final matrices that we found in the last video. The one on the left is the final distance matrix, and the one on the right is the final root matrix. Now the distance matrix tells us the weight of the shortest path, and the root matrix helps us find that path, which is particularly useful if it's not direct. So for example, if we want to find the shortest route from A to B, we can see from the network that to go there directly it's got a weight of 9, but if we look at our distance matrix A to B, we can see that the shortest path has a weight of 8. Now in order to know which way we go, we look at the root matrix. So from A to B, we go to A, and we go to column B, and we can see that the first vertex we must visit along the way is vertex C. So if we start at A, we can see that we must then go to C. So then we go down to the left to C, and we still obviously want to end up at B, so we go along to the B column, and we can see that the next vertex we want to visit is E. Okay, then we go down to the E vertex on the left, and obviously B is still our destination, and we can see that B is the next vertex we arrive at, so that must be our destination. So our shortest path has a weight of 8 and starts at A, then goes to C, to E, to B. So if we look at our network over here, we can see that A to B directly is 9, but if we go from A down to C, down to E, and then up to B, that has a weight of 3, 4 plus 4 is 8, which is what our distance matrix told us. Obviously these matrices are really useful if the network is far more complicated than the one we have used in our example. Okay, let's look at a different route. Let's say B to D. It's worth pausing the video at this point in time for you to find the shortest path from B to D using the root matrix. Okay, so if we look at the distance matrix, which is this one on the left, we can see that to get from B to D, again we have a weight of 8. Okay, so let's go over to the root matrix. Okay, so we start at B, we know our destination is D, so we go to the D column, and we can see that the first vertex we hit is E. So we start at B, we go to E. So then we go down on the left to E, we go across to the D column again, and we can see that the next one we go to is C. And then we go over to C on the left, we go to D column, and we can see that D appears, which means we must have found the shortest route. So the route is B, E, C, D with a weight of 8. And if we just check on our network, so we go to B, go down to E, go up to C, and down to D, we can see that's 8, and there was no direct link anyway. Okay, let's look at the shortest path from A to D. Okay, so we go to distance matrix, up to A, we go along to D, and we can see that it has a weight of 5. Then we go to our root matrix, so at A, we go along to the D column, and we can see that actually D is the first vertex we get to, which is the end of the path as we have arrived at our destination. So AD is a direct route of weight 5, and that is the shortest path. There are a number of points to consider when implementing Floyd's network. First, just make sure you're aware that the number of iterations required is always the same as the number of vertices in the network, even if no changes are made during one iteration. Floyd's algorithm is very time consuming, so you might be asked to do the whole thing on a small network, or perhaps just perform one iteration on a larger network. It is really easy to make a mistake with Floyd's algorithm, so be very careful. It is very fiddly, and perhaps a highlighter will help. Always make changes to the root matrix as you go along, and it's really important you know how to interpret the final matrices. So that concludes this section on planarity and Floyd's algorithms.